Hello, my name is Andre, and I'll be introducing my work on estimating predictive uncertainty via prior networks. We have the following scenario. We have a model, and we'd like to obtain measures of uncertainty in the predictions of our model to take actions such as accepting or rejecting the prediction or deploying active learning. Crucially, we'd like to know why the model is uncertain. Is the model uncertain because we have an input from region of severely overlapping classes, a known unknown, or is the model uncertain because we have an out-of-distribution input, an unknown unknown? The theoretically motivated way to do this is via measures of diversity of ensembles. Consider an ensemble of models sampled from a posterior distribution over model parameters given the training data. The predictions of this ensemble should be consistent in domain and diverse out of distribution. This behavior can be visualized on a simplex. And crucially, an ensemble can be considered to be a set of draws from a distribution over output distributions. By placing a posterior distribution over model parameters, we're inducing a distribution over conditional categorical distributions. This is equivalent to inducing a distribution over output distributions conditioned on X, which is a distribution over a simplex, and the ensemble is then a set of draws from this distribution. In this work, however, we will be explicitly parameterizing a distribution over output distributions by using a neural network which parameterizes a Dirichlet distribution called a prior network. We will then train this prior network to have the following three behaviors of a distribution over output distributions. If the model is confident in its prediction, it should yield a sharp Dirichlet distribution at the corner of the simplex corresponding to the target class. If the input comes from a region of severely overlapping classes, the model should yield a sharp Dirichlet distribution at the center of the simplex corresponding to being confident in predicting flat categoricals. And finally, if we have an out of distribution input, the model should yield a flat Dirichlet distribution corresponding to the model thinking that any categorical distribution is equiprobable and not really knowing what to do, being very uncertain. The argument we're making is that training a neural network to yield the following three behaviors is easier than inducing a distribution over distributions with the following behavior by appropriately choosing a prior over model parameters. The latter is very challenging, while training a neural network is far easier. Other advantages is that this approach is now computationally far cheaper, and any measure of uncertainty can be calculated analytically. In this work, we showed that prior networks are capable of distinguishing between known unknowns and unknown unknowns, and furthermore, they outperform ensembles generated via Monte Carlo dropout on the tasks of misclassification detection and out of distribution input detection. If you're interested in hearing more, please visit me at my poster or contact me in any way. I'm looking forward to seeing all of you. Thank you.